Karlis. I work for CERT.LV, mainly as a reverse engineer. So my topic of this talk is basically, we always say to the users that they should not click on links, they should not click on attachments. So this is basically how you should open an attachment the proper way. So that's a warning of this whole session. So this is a CERT technical session. So there will be no fancy blinking lights, maps, diagrams. I have no cartoons, I think. So this is purely technical stuff. So that's the last opportunity for you to escape to some other tracks. And now we proceed with some technical joyride. So setting the scene, we have the incident is a spear phishing incident. So one new email arrives. Please see the document attached. I don't know. I didn't investigate the spear phishing part or the email part which incites user to click on attachment. But there's an attachment. Let's say readme docx. So readme docx. Well, docx file can be anything. Let's check it out. What it is. This time it's really an Office XML file. That's okay. That's legit. We go on. Let's look at metadata. The EXIF tool output doesn't show anything very suspicious either. Maybe the total edit time of 1 minute. So either it was a fast typer who typed the document, or well, it was maybe just the tool doesn't support the total edit time functionality. Well, we know that docx files are just zip archives of a directory, so we can unzip it and see the internals of the document file. Unzip, and there we see an image EPS file. So, well, you always start looking at the images first, right? You know, that's the most interesting part. This will be a slide which repeats itself over and over, and we're just putting new information on this roadmap or map or sketch or whatever, how you want to call it, but we will fill this slide up. So we have the container with the Office document, then there inside is an EPS image. Okay, let's look at the image. Well, we don't want to look it as an image. Let's just cat it and look it in text mode. There is quite some a small header of like human readable part with some token, pop exchange, whatever, and then comes like a huge hexadecimal part, which takes like 99% of the file. So it's altogether like a 700 kilobyte file. 99% of it is unreadable currently. So if you take a closer look at it, and if you have done something with malware before, you can see that, okay, there is some hex here, there is some hex here, and there is an XOR command there. So you can just go ahead and try to decrypt this with this key, and it works. But you can also do some small, quick reverse engineering of this image file. You can do some formatting, because before, this is basically one long line, which is not human readable at all. So you do some formatting, indentation, like new lines, indentations, then you rename the variables and functions as you feel is a correct way, because they all have just random names like A3, A2, A1. And then you can see that, okay, this function is basically parse as PostScript. Then this is the encryption key. That's the decrypt function. It's symmetric. And below here, this is basically any management level person can understand. This is ciphertext, decrypt, parse, execute, quit. So it's almost poetry in PostScript, I would say. Okay, so another level, a deep one level down, we had the outer PostScript image, and inside we can get to the inner PostScript part. So I wrote just a quick and dirty Python script to decrypt the inner PostScript, 3 lines of code or something. We know that this is PostScript 2 because it's interpreted and executed as PostScript. So it's 700 kilobytes of text, or like 187 pages of A4 in like standard print. So I can go on and start reading. But that's not the way I approach. So you can do high-level analysis or basically just zoom out. And humans are very good at pattern matching. AI is, I think, not as good yet. So you can go line by line and read and get crazy. Or you can just see that, OK, here is something that sticks out, and here is something more that sticks out. So you just go and focus on those places which stick out. And, well, good enough. So this part that sticks out to any reverse engineer, that's very obvious. It starts with 5.5, 8b, EC, and so on. And that's how you start a new frame in x86 assembly in cdeclare. So basically, that's the start of a function. So that's code, that's shell code. So when you interpret it as code, as x86 code, you get like 5.5 is push base pointer, 8b EC is moving stack pointer to base pointer, and so on. So with persons with some assembly knowledge, this is what you know and do. And this part, well, I didn't investigate it myself, but it was possible to find some analysis online that it's basically CVE 2017 something that's basically the PostScript engine exploit. So we got one level down. We have shellcode now. So what to do with shellcode? We can convert it to binary, save in file, and open it in IDA Pro. So as usually, for malware, the shellcode is packed. So the small blue line here is the part of the executable of the shellcode that IDA was able to interpret as proper x86 code, and the rest is uninterpreted, so the binary part which is packed. So we have an unpacker, which looks like this from the flow diagram. And it does the unpacking, so basically decrypting all of this and then running. So at the beginning, somewhere here, it finds where it is in the memory. Then it finds the location where the packet data starts, the data which was not interpreted by IDA. And then I see some magic immediate constants. So this 9908 like this doesn't make any sense at all, either in hex or in decimal. Neither does this, neither does that. But constants, magic numbers are always a good starting point to understand code, and Google helps. So if you just Google for those hexadecimal numbers, all the hits are about Mersenne twister. So it's a PRNG, it's a pseudo-random number generator. So it's part of the decryption routine. We also can identify the seed for this algorithm, so we can recreate the decryption routine. And then after the malware unpacks itself or decrypts itself, this decrypted code is called. So basically, there is a call to this to the location which was unpacked. All right. So that was just looking at the shellcode. Now we want to execute it. So we could write another program, a small script that decrypts the payload, this packet part. But an easier way is just to use the same code as we have, because shellcode, it's x86 code, it's runnable, it unpacks itself, but it's like a engine, a standalone engine. Even if you have gasoline, you can't start it. You need some wires and whatnot to start it. So it's the same with shellcode. You need to wrap it around into small, with small assembly code to be able to run it. Okay, I skipped the technical details, but it's several ways how to do it. And then we have the inner shellcode. So we successfully decrypted it. So the outer shellcode, as we saw, it includes the inner shellcode. And there is the exploit part. So now we have unpackaged shellcode, so unpackaged x86 code. Where do we start? It's 700 kilobytes. No, it's less, I think, like 200 kilobytes. But still, it's a huge piece of code. So how to start? One way to start is with strings, because it's a human-readable part of the code. So let's run the strings command. And then there are a lot of strings, but some are interesting, so I just grabbed for this. So there's 3 occurrences of this program cannot be run in MS-DOS mode. So that's part of the PE header. So that basically means that there somewhere in this shellcode there is executable code at those offsets. So 870 hex and 2348 and the other one. So great, executables are always great. We can run them, we can debug them easily. If we look up in hex viewer, so here is this program, offset 870. This program cannot be run in MS-DOS mode, and so a few bytes up, MZ, that's how portable executable, that's basically how exe and DLL files start, that's a header. So we know that at this offset, an executable file starts, and in fact later I found out that basically those 2 other executable files are included within the bigger executable file. So we can put another layer on our map. We found out the executable file inside the shellcode, and inside that executable file there are 2 more executable files. So if this all somehow, and it's all somehow stacks together. Okay, so the first real executable, finally. So it is a real executable. We can test it with file. File says that it's a valid P32-bit executable. And in fact, it's a DLL file with 2 exports, so 2 functions which can be called out of that file. One of them is DLL entry point, which looks benign after some time being spent investigating it. So the other entry point is likely to be the malware entry point. If we follow the normal logic of malware, so this should be the dropper. This should be the component that runs and writes something to file system and creates a persistence. So what does it do? It checks for 32 or 64-bit environment, so whether it's a 64-bit or 32-bit operating system, and then it runs the appropriate exploit for escalation of privilege exploit. So those 2 executables here, in fact, are escalation of privilege attacks for 32 and 64-bit operating systems. Okay. So now we come to dynamic analysis. So running that executable file, or in fact debugging it. It has a few imports. So everything that is malware specific is loaded at runtime to be, I guess, to be less suspicious or be more stealthy. So here we can see like hidden use of NT-DLL. There's a hash value being provided as an argument to a function that basically searches for DLL handles. So how did I find out? I just started execution here, push the value on the stack, the argument on the stack, then run this function, and then see what is the output of it. And then, because at the beginning everything is just numbers, so there are no meaningful names. All the meaningful names I have added myself. So you run that function, you look for its output, and well, it just returns handle of NT-DLL. So well, I just say that that's good enough. That will be our DLL, resolve DLL from hash value. So everything here is hash-based, so there are no strings at all. So in the same way, it searches like it searches for some hashes within DLLs. So this is like search for hash value in DLL. You provide an argument, which is a hash value, and the outcome is the address of or the entry point for like syscall for NT-allocate virtual memory, which is a pretty evil function. So if you just run strings, you will not see anything. You have to go deeper and try to understand what the executable is doing. Well, how to defeat this technique? You can either run in debugger and just run by hand all those places where this function is called. Usually it's not so many places. Or you can just write some IDA Python scripts if you know those, if you have some tables with hash values and corresponding names. Okay, so what does it do next? What does executable do next? To be more stealthy, it searches for Windward XZ process. Remember that it was a document file, so most likely, well, the Windward process should be running, which opens that document. So then it allocates new memory under the Windward process, copies itself in that process memory space, and starts a remote thread. That's pretty typical for malware. And then it does, once it's in the running under Windward process, it does lots of string decryption. So strings are not visible, but they are decrypted dynamically. So there's a string decrypt string function, which on output, here is an argument to it, some random garbage, and then you run the decrypt, and then it says system root / system syswoe64. So once you identify the places what malware authors want to hide, that's the places you want to look at. So it's kind of an dual-edged sword. You know, they are hiding it, but then once you know which functions they use to decrypt strings, you can go and see which strings they are hiding. So that means those are the most valuable strings for them. Okay, so once it's running under Windward process and has unpacked or decrypted those strings, it does zip decompression, then it writes file, it establishes persistence by modifying Windows registry, and then it launches the dropped malware. So if you don't resolve the function name, all the function names, then you see something like just call foo, call blah, call something else, and you don't understand anything. So you need to go step by step, resolve those pointers to proper names, and then you can start to understand, and it becomes quite easy to understand the functionality of it. Okay, so zip decompress, something interesting. So in here, it decrypts string RTL decompress buffer, which is a Windows system call for zip decompression. Then here it loads NT-DLL. So here you can see it's just a string NT-DLL is passed to load library, and after this is executed, the handle of NT-DLL is stored in this local variable. So the decrypt string function is, here you can see that here is an encrypted string, and here is the length of it. So 14 hex, that's like that's 20 bytes, or 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it should be 19 characters, and then the trailing 0, so 20. That's the length of it, of the string. Okay, so once it loads in this stealthy way this NT-DLL library, it calls get procedure address with a parameter RTL decompress buffer. So basically here it finds a pointer of the syscall, and then later it will execute it. So we still want to find the payload, the real thing that ends up running on your machine. So we can debug, break on start, and then just manually set the instruction pointer to where the remote thread start function starts, and then put a breakpoint where the decompression is called. We want to know what is decompressed and what comes after the decompression. So yeah, we just put a breakpoint here, and then we'll be able to see what comes out of decompression algorithm. Okay, just to jump one step over, so we see that we find the payload after this zip decompression, and before that, it's in fact another layer of encryption which I found too. Are we there yet? It's only 4 minutes left. We are almost there, but not yet. So we finally found the payload. So that when zip compression or decompression is done, inside there is a DLL file with one export DLL entry point, so it must be the evil part, without any interesting strings, but with some import table entries which look malicious. So if you see a WinSocket 32 DLL imported, it means that that piece of code uses network functionality, which is likely to be true for malware. So finding the crown jewels, finding command and control. First, we need to find the string encryption function, which is at the very beginning of the DLL entry point. So here's a create mutex. Mutex is like a, okay, well, mutex is mutex. Never mind, it has a name. So where does the name come from? Create mutex is a parameter name of the mutex. It's register EDI. Where does EDI come from? Move EDI EAX. So where does EAX come from? EAX comes from decrypt string. So this is a string function. We can run it all the time, see all the strings what malware is hiding. So this is how the string encryption function looks like. Just kind of a loop with some XOR, so it's typical crypto stuff. So, and here is the crown jewels. So here's a call to decrypt string. So in a loop. So first time it decrypts google.com, and second time around it encrypts wmdmediacodex.com, which sounds kind of malicious, and it is really the command and control of that piece of executable. So overall, you see all the layers we went through one at a time, going deeper and deeper and deeper. And that's basically the most, or the deepest part, what we explored. So yeah, I think I'm maybe like 1 minute left. So I'm open for questions or comments. So of course it was not a 30-minute thing we did together with my colleague, but yeah, I tried to compress and show you the way how to open email attachments the right way.
Questions, anyone? We have time for at least 2 questions. No question about what is mutex. Are you asking what's mutex?
How much time this analyst take?
The first time, I think we spent a few weeks, but not like 100% of the time. I think so. The question is like, what is the skill set for the person who is doing it? So if he is just like a mouse operator, then forget about it. If he has like some decent knowledge, then first time it probably takes a few weeks. But if you have seen this sample before, or similar samples before, and you have prepared your tools, it probably takes like half a day, or maybe less. So it decreases quite quickly. So the learning curve is quite, I don't know, steep, or yeah. So I think if you get like I don't know, third time sample of the same family, then you have your scripts prepared, you just run them, and that's pretty quick.
Hello. Are you happy in the moment when someone presents you a new sample to analyze, or go, ouch, again?
I think you should be happy when you see things. Because when you don't see things, it means you're not good enough. I mean, it's not that when you don't have samples that nobody is attacking you, it's rather that you're not just skilled enough to even catch them. So yeah, I'm happy when a new sample comes in. So I know that sample didn't go into production and is not causing damage. So
Please send samples to Karlis. I have one question from my side. In your slides, we saw that the one executable contained 2 other executables. What was the purpose for each of those?
Okay, so here the dropper was running a test to fingerprint the environment. So whether it's a 32-bit or 64-bit operating system, and then it just ran one of those respective exploits to break out to kernel privilege level, because it was still running under word privileges, and it needed to break out to system privilege to modify the Windows registry and do all the bad things.
Well, thank you for the answer. Let's give applause to Karlis and some sweets.
Sweets, thank you.